point. Just like starting the lecture.
Okay.
So we're happy to have the Debapratim Banerjee from video science. He is going to talk about universality. Debapratim did undergraduate and masters of science and then did PhD University of Pennsylvania. And he's back as inspired faculty. So this is an area which is reasonably hard in Catalan problems of this region, especially
Yeah. So I first of all sincerely thank you for inviting me to giving me this talk. Inviting me to give this talk. So today I am going to talk about a new combinatorial approach for a universality of Wigner matrices. So okay, I'm sorry. Okay, so this is a brief overview of this talk. So at first I give some introduction about what random matrix theory is, and then we discuss some primary notations and concepts, and then we give the formal statements of the result. And as this paper is quite long and technical, I will only be able to give some ideas of the proof, but not at all the whole proofs. And then I will summarize what I said. So to begin with, what is random matrix theory? According to the best of my knowledge, the study of random matrix theory started with the seminal work of Wigner in 1955. Here he considered a large dimensional symmetric matrix with the upper diagonal part IID mean 0 and variance 1 random variable, and was interested in the eigenvalues of the matrix as dimensions grows to infinity. One of the first questions of interest here was about the limiting property of the empirical distributions of the eigenvalues, or if you look at the histograms of the eigenvalues, what is the limiting property of this? This is currently known as the semicircular law, and this is very famous. As time progressed, several fine art questions came into interest. To discuss this problem in the next slide, we shall consider some preliminaries. So let's see what is an Wigner matrix formally. In this talk, we shall consider a n cross n symmetric matrix and call it Wn, and this will be the Wigner matrix with entries given by xij by square root of n, where xij's are IID with mean 0 and variance 1, variance 1/4, and we shall soon see why instead of 1 we take 1/4. This just makes the analysis look a little bit nicer. Otherwise, we have to scale the factor by 2 to the power, a very large power at every step. So that's why independent and identically distributed. And we call this matrix a Wigner matrix. A special case of Wigner matrix is known as the Gaussian orthogonal ensemble, or GOE, where xij's are normal 0, 1/4. So instead of just mean 0 and variance 1/4, we take normal 0, 1/4. And xi's are Gaussian with normal 0 and variance 1/2. We call lambda1 n, lambda nn to be the eigenvalues of Wn, and lambda this bracket 1 n to lambda bracket n, n to be the ordered eigenvalues. So the joint distribution of the eigenvalues of the GOE is given by, for GOE case, the joint distribution is known. So this density function is given by this formula. So this is completely explicit. So these are the preliminary notations and the things we need. So I will just briefly talk about the problem of age and bulk universality. The problem of universality arose from the question of investigation of joint distribution of the eigenvalues of the Wigner matrix. As a starting point, one looks at the GOE as the joint distribution is explicitly known. And it turns out there are two kinds of behaviors of the eigenvalues. Firstly, when an eigenvalue is typically within the support of the semicircular law. So in particular, the histogram converges to the semicircular law. And when an eigenvalue is typically in the interior of the semicircular law, this a kind of behavior is observed. And secondly, when an eigenvalue is near the support of the semicircular law, so semicircular law has we'll just see the definition in semicircular law in a few slides, but yeah. So when the eigenvalues are near the boundary of the support, a different kind of behavior is observed. So universality question asks whether this behavior remain valid even when the entries are not Gaussian. So in this talk, we shall mostly consider the problem of age universality. One might note that for the GOE case, as the eigenvalue distribution is explicit, the behavior is known by the explicit behavior of the eigenvalues near the edge is known by the seminal work of Tracy and Wigner. So there are mainly two approaches to prove the edge universality. Proving edge universality is in general a hard problem. There are two main approaches for proving this kind of result. Firstly, like by a detailed analysis of this resolvent kind of matrix, which is given here. And this method is well implemented by a series of works by Dosh, Yao, and their group. And the second approach is a very fine analysis of the high power of the trace of the matrix. This was initiated by Shinai and Shoshnikov, and from there on, Shoshnikov wrote several papers on it. In this talk, we shall take the second approach and discuss it in a bit detail in the next slide. In a paper by Shoshnikov, the combinatorial approach for edge universality was initiated. The basic idea is to analyze expectation of trace of Wn to the power 2t n to the power 2/3 for every possibility and show that limit is bounded for t. This is the reason why one scales the Wigner matrix by 2 as to cancel out the growing power of the 2 to make this expectation bound. Okay, so here everything is scaled by 2, right? Wn's entries are scaled by 2. So semicircular law has support to -1 to 1. So you take the expectation, and expectation as n grows to infinity. So you know yeah. Okay. So once this is proved, then it can be proved that this limit is the Laplace transform of the point process at the edge. We will not define the point process of the edge formally here, but we will see what we mean by that. So which recovers the limiting one-point correlation function. This will again be defined formally. And for general k-point correlation function, we will again define later. One looks the joint expectation of this, and these two limits, as intending to infinity, determines the full point process at the edge. So this is the main idea of Shoshnikov. So take a large power like of order n to the power 2/3, and take the Wigner matrix and analyze the expectation of this trace and analyze what properties are of it are useful and what properties of it are not.
Why is it called the combinatorial?
So these you have to do a lot of combinatorics to count these things. We'll see why it is called combinatorial approach. So there are several. So this is a honest criticism of the existing combinatorial approach and novelty of our work. In my limited knowledge and understanding, there are several gaps in the paper by Shoshnikov. The main idea of Shoshnikov is to map the contributing tuples known as what. We will again define this later. So I am just giving an overview of what I did. So uh, I will define this later in detail. So two Dyck paths. Those who know the combinatorial proof of the semicircular law might find it obvious, but however, unfortunately, when we are dealing with such a large power, this map is not at all obvious, because for combinatorial approach, you take also this trace of wn to the power 2k, but k is fixed. Here this power grows at a very high speed. So this map is not at all obvious. And in Shoshnikov's paper, this map is nowhere explicitly constructed. In the current paper, we have constructed such maps. So, and the image is indeed a Dyck path at the end. However, this map is not at all obvious and not one-to-one. So what we have to do, we create this map and fix a Dyck path and count how many words there are which in the inverse image. So that's the strategy to do that. So we shall try to give the idea of this map and what we do in the later part of the talk. In our paper, we explicitly construct the map and provide a bound to the inverse image of the map, just as I said. One of the major assumptions, also the second, another novelty of this work is one of the major assumptions of Shoshnikov is that they assume the entries of the matrices to be symmetrically distributed around zero. This is due to the fact in a Dyck path, every edge is traversed even number of times. So we'll see why again. In this paper, we extend our approach to possibly non-symmetrically distributed entries. We'll see. And although we use the and third thing is, although we use the GOE result to prove the limit of the expectation of the mentioned quantities. So by the mentioned quantities, I mean the quantities here, these quantities and these quantities. So they actually are in limit the Laplace transform of the correlation functions. So by Tracy and Widdom's work, this Laplace transform converges. So we have used this, that the limit of the expectation of the mentioned quantity to exist, but I strongly believe that the existence of the limits can be proved naturally. So this might give an alternative description of the Tracy-Widdom law. So yeah, sure. Yeah, sure.
See, product that you can understand TI. The next term after subtract, is it TI or T is the sum of TI?
No, TI. So we center it. Huh?
It doesn't matter which I you get. Oh, I see. Whole thing is in product.
Yeah, whole thing is in the product. Is it okay?
Yeah.
Okay. So we keep it as an interesting future research. Now we define some preliminary notations and concepts. So first we start with the correlation function. So for this point, recall the joint distribution function of the GOE. So let's go back. So the joint distribution function of the GOE is given like this. Okay. So the k-point correlation function is defined as this integral. So this is another way to look at the joint distribution function. So I am not from a physics background, but I think physicists find it more comfortable to work with these functions instead of joint distribution. But I do not have any idea. Yeah. So let for any interval I, nu n be the number of eigenvalues in the interval, and then it can be checked that this expectation is just given by the integral over over the k point correlation function. So this is somehow you take an interval and find how many eigenvalues are in that interval. As mentioned earlier, there is a different kind of behaviors of the eigenvalue at the edge. In this in this slide, we shall try to give a formal explanation of what we mean by that. By the limit, we shall formally mean the convergence of the k point correlation function as n converges for every k. One might see that this determines the joint distribution functions of the eigenvalue. However, we need to rescale and recenter the eigenvalues, in particular, recenter the eigenvalues. In particular, for the eigenvalues near the edge, we consider the following recentering and scaling. So, the support of the semicircle law is +1 to -1. So lambda in, we just write it like this. And whenever lambda in is greater than 0, and lambda in is equal to -1 yin whenever lambda in is less than 0. It can be proved by that the 1-point correlation function at the edge is order n to the power 2/3. This is the common intuition given for pseudo law. So if you are interested, I can give a two-line heuristic for that. Oh, I just take the lambda in and I define yin this way. Yeah. So if you are interested, I can give a two-line heuristic, but this is just okay. But if you want it, I can give it later also. Yeah, because I need the semicircular distribution density, which I am going to define within 2 slides, but it is fine. So instead of considering this rho n 1, this is not very explicit, but we shall consider the following to make our life simple. We shall consider the following rescaling and centering instead. So we consider lambda in equal to yin by 2n to the power 2/3. And lambda in, if lambda in is greater than 0, and we consider lambda in equal to -1 minus yin by 2n to the power 1/3 for lambda in less than 0. Okay, so this is the rescaling and centering. So the key idea is simple. So we fix t and prove that the quantities are here. So these quantities, like the expectation of trace of these quantities and expectation of these joint quantities are of order 1. Once this is proved, it can be proved by some elementary calculation. So these calculations are not hard. You can prove that this expectation is just 1 plus small o of n to the power -1/3 into the Laplace transform of the correlation functions. So it is not exactly correlation function, but it is fine. It is one end at the one rightmost point or the leftmost point. So semicircle law is supported in -1 to +1. So this is either it put mass only on 2 parts. So either +1 or -1. So this is, and in general, so in particular, you can reconstruct the, so let's see. So here Rnk1 is the rescaled correlation function. So Rnk1 is given by these quantities. Rnk1, so yi's are the recentering and rescaling. So yi's are how I defined, and Rnk1 are the rescaled correlation functions. So if you prove that this thing converges, so this the Laplace transform of the Rnks also converge, and as the Laplace transform converge, they determine the limit. So you find that you find that the actual rescaled correlation functions are also converged. So this is how the proof goes. So this is by post inversion formula that Laplace transform determines the actual function. So by using post inversion formula, you can check that the actual correlation functions also converge. The general K case can be also proved by the convergence of general moment. Here we have used that also the RNK1 converges for the Gaussian case. And in order to prove that universality, that task boils down to analyze the very large power of the Wigner matrix. This is also the reason we scale everything by 2. Otherwise, the expectation we have will blow up at every step and we have to do some adjustments. We also need to prove that the final limit only depends on the first 2 moments of the random variables, provided they are sub-Gaussian. So this is how things are done. So we prove that the limit exists and the limit only depends on the first 2 moments, provided these random variables are sub-Gaussian. Where sub-Gaussian comes into play, this is another story, because we have certain error terms which goes to 0 if you have sub-Gaussianity. But if you want to move beyond sub-Gaussianity, you have to use a truncation argument. Then it will be again a difficult problem. I haven't checked that. So in general, it is known that edge universality holds beyond sub-Gaussian. So but for our proof, we require sub-Gaussianity, because certain error terms converges to 0 only if things are sub-Gaussian. So let's formally define the semicircular law. It is a distribution on -1 to +1. So it has density like this. And the Catalan numbers are well known in combinatorics. So 1 over k plus 1, 2k ck. Actually, this is the 2 to the power 2k times the 2k moment of the semicircular distribution. So, and Dyck paths are paths of simple symmetric random walk, which starts from 0 and returns to 0 after 2k states and stays on or above the x-axis. This count is given by ck. So these things are well known in mathematics. And also in this paper, we require the generating function of the Catalan number. So this is given by this, and its power. So c to the power mx is given by this. So the coefficient of the powers are explicitly known also. So these are standard results I am using. So let's talk about a little bit about combinatorics and how combinatorics comes into play in this problem. So in particular, observe that trace of w to the power k is just I0. So you can expand this. So I0, I1, Ik minus 1 to I0, and sum over this tuple. So the combinatorial approach depends on analyzing this sum systematically. So we will introduce some terminology. So in particular, a tuple I0 to Ik minus 1, I0 will be called a word. So this is a terminology. And since we have to analyze the quantities Ij, Ij plus 1, so in particular, this is I0, I1, and there will be I1, I2, and so on, as they represent the random variables. We naturally associate a graph to these words. So this is given by GW equal to VE, where V is this set I0, I2 to Ik minus 1, and we put an edge between Ij to Ij plus 1 for every j. So we start with a tuple. We construct a graph in the following way. So we consider this set I0 to Ik minus 1, and we put an edge between two vertices if they are Ij, Ij plus 1. And in particular, this will be a multi-graph in general, because several random variables in this product, several one random variable can appear several number of times, and so every edge can be repeated multiple number of times. So this will be in general a multigraph. One thing to note that an exploration, what is an exploration on that graph? So for example, if you at the end of the day, we have to kind of work with the tuples, not exactly graphs. So this is an exploration of the graph. So we start with I0 and then we go to I1 via an edge. Then we go to I1 to I2 via an edge, and so on. So this is an exploration of the graph, not the exact graph. So instead of graph counting, we have to count the exploration, number of exploration of that graphs. So let's begin the formal statements of the result, and I will go a little bit deep into how things are proved. So these formal statements of the results are as follows. Suppose Xij's are IID sub-Gaussian random variables with expectation of Xij is 0 and variance is 1/4. Then for any t, this lim sup is bounded, and lim sup of Wn to the power 2 t n to the power 2/3, and these expectations, this is bounded and this goes to 0, and this lim sup is also bounded. Further, the further in the first and second equation, words where every edge is repeated exactly twice give the dominant contribution. So recall that the edges in the graphs represent the random variables. So hence only second moment matters, because in the dominant contribution, all random variables appear exactly twice. And random variables are independent. So in the product, this expectation is 1/4 to the power something. So the number of random variables. So hence this limit only depends on the first and second moment. The limit first moment is 0. Limit this lim sup only depends on the second moments of the random variable, and there is a combinatorial coefficient by counting the number of exploration, how many exploration are there. So this makes these coefficients makes things hard. So sorry, it is known that the limits in 1 and 2, I proved that lim sup is bounded. So it is known that the limit in 1 and 2 exists for GOE from the exact calculation. Hence the limit exists and is universal, because only the second moment matters, and for Gaussian it exists. So hence the limit exists and universal. As a corollary, we get the edge universality of the Wigner matrices. So these are the main results. So now we will give some ideas about the proofs. The fundamental idea of the combinatorial proof of the LSD is to map the words to Dyck path, where every level of the Dyck path has a label. So let's draw. I will draw it in a moment. With slight abuse of terminology, we call this label Dyck paths also Dyck paths. When we consider the trace of a finite power, a certain class of words dominate the expectation. These words can be mapped to Dyck paths naturally. We shall discuss the map here briefly. We start with the Dyck path and follow the random walk. Every time we go up in the random walk, we create an edge. Every time we go down in the random walk, we close an edge. Following is an example. So let's give an example. So we are dealing with level Dyck paths. So where is the cursor? Okay, we are dealing with level Dyck path. So say first level is ground level is 1. Then we go up in the Dyck path 2, and then we go up in the Dyck path again 3, and then we go up in the Dyck path again 4. I am drawing a very simple Dyck path, and then we come back to 3, and then we come back to 2, then we come back to 1. So this is a simple Dyck path. And what is the word? So the word is look like this. So we start with 1. Freeze. We start with 1. Then we go to 2. Then we go to 3. Then we go to 4. Then from 4 we come back to the level of 3. So we come back to the level of 3. Then we come back to the level of 2. Then we come back to the level of 1. So this is the word. And what is the graph? So we start from 1 to 2. So this is an edge. Then we consider 2 to 3. So this is an edge. Then we consider this is 1. This is 2. This is 3. Then we consider 3 to 4. This is an edge again. And then we consider 4 to 1. This is sorry. Then we consider sorry. Then we consider 4 to 3. Then we consider 3 to 2. Then we go back from 3 to 2 to 1. So this is how the graph look like. So however, observe that there are certain constraints in such words. For example, any word must close the immediate open edge as the random word do not jump. So for example, when we are here 4 to 3 and we need to close an edge, we cannot jump, right? Because the next step, if we need to close an edge, we have to close this 3-4 edge. We have no choice. But there are words, however, when we consider the large power of trace, for example, of order n to the power 2/3, this no longer remains true. Many words have a non-trivial contributions which cannot be mapped to Dyck paths naturally. Perhaps the easiest word of this kind is as follows. Instead here 1 to so we consider this 1 to 2, 2 to 3, 3 to 1. Now instead of closing 1 to 3, we want to close this edge 1 to 2. So we cannot close it here because otherwise we are closing 1 to 2. So what should I do? So instead of closing this edge, we'll jump to this level and close 1 to 2, and then say we close 2 to 3, and then so this is 2, this is 1, this is 3. And then we come to 3 to 1. So this is a valid word, right? This is a valid word because it starts from the vertex, it comes to the vertex, but it jumps. So this main idea of this talk is to explore where these jumps are. So this gives us that inspiration that there might be a non-trivial map from words to Dyck path, because if we follow the simple random walk pattern, we cannot map these kind of words.
You have one order power.
So you can yeah. So the word is like this, right? 1, 2, 3, 1. It can repeat here, right? Whenever you create a new edge, you go one step up. That convention will be valid. No, we start with the word like this: 1, 2, 3, 1. Okay, that explains this part. Then instead of going to 1 to 3, we go to 1 to 2. Then we go to 2 to 3, and then we come. Which one? Yeah, that will be again, but our convention is like this. This 1, 2. Whenever we close an edge, we match these things. That can be done, but that count will be rather messy. No, they are the levels of the particles. Yeah, that's the idea. One advantage of the map, we are able to map words with some edge traverse what number of time instance. In this case, some steps in the Dyck path will not be covered. So, for example, if we just had this thing 1, 2, 1, 2, 2 to 3, 3 to 1, then we stop. Then we do not need to cover this part. This is also a valid word, but we do not cover the remaining part of the Dyck path. So in this case, all these edges are traversed exactly once, and we do not need to cover these parts. So let's describe the mapping of the words to Dyck path. This map is recursive in nature, and this is done in the following steps. We start constructing the Dyck path according to the exploration of word, and we continue until we arrive at a situation such that we have to close an edge which is not the immediate one, as we saw. And in this scenario, we jump to the level of where we need to close the edge, and we close the edge, and hence we arrive at a different level, and from the different level we go back to step 1. So this is a recursive map, and the process ends when all the edges are covered. So this is the first observation. Whenever we jump between different levels, they has to have the same level as they represent the same vertex in the graph. So if you look at, so suppose we jump from this vertex to jump from this level to this level, they have to have the same level because they represent the same vertex, right? Because 1, 2, 3, 1. So then we go from 1 to 2. So they have to represent the same levels. And the observation 2 is a little bit complicated. Let's draw a picture and we'll see. Let's consider 2 different words. So the first word is like this. First word is 1 to 2, 2 to 3, 3 to 1. Here we do not jump. Then 1 to 3, and then 3 to 2. Then we go to 2 to 4, and then we go to 4 to 3 again, and then we go to 4, and then we go to 4 to 2, then we come back to 2 to 1. So this is an one edge, and let's consider another word which has the same Dyck path but it jumps. So let's see 1 to so we start from 1 to 2, then we go from 2 to 3, then we go from 3 to 1, and then instead of coming back, we close the edge 1 to 2 here. Sorry for my drawing. 1 to 2. Now we create this edge 2 to 4, but we do not create this edge here. So if we create an edge here, it will not be a Dyck path anymore. So instead of whenever we construct a edge from right to left, if we at the next step, if we create a new edge, we create it here. So in the left of that part. So we create an edge here 2 to 4, 2 to 4, then 4 to 3, then 3 to 4, then 3 to 4, and 4 to 2. Now we are at the same level. Now we close this edge 2 to 3, and then at the end step we close 3, 2, 1. So this is a different exploration, but gives the same Dyck path. Sorry for my bad drawing, but this gives a different exploration. This is the same Dyck path. So these two words are completely different, but they have the same Dyck path. So in this map, so the main idea is like, okay, we start with a Dyck path, and how many words are there which maps to these Dyck paths. So in order to understand the most significant part of this paper, is to understand the jump of this map in the systematic way. For this, we introduce the following definitions. We start with a Dyck word W and map it to the Dyck path according to the previous slide. We call an instant to be of type J if at that instant we create an upward edge and the vertex corresponding to that instant appears for the jth time at the right endpoint of the upward edge. We'll see an example, just the example I draw just right away. Okay, let's see an example. So here, when we consider this 1, 2, 2, 3, 3 to 1, so starting vertex is a little different. So let's consider this one. So this 3 here has appeared as the right endpoint of the upward edge exactly twice. So this is a type 2. This is a type 2 instant. And this one is also a type 2 because it has like we imagine as this is the starting, we imagine a imaginary upward edge here, and this is also we consider a type 2 for counting purpose and every purpose. So this is also type 2. So these are the, like in general, if you have appeared at different levels for 3 times, then it will be type 3 and so on. So now at type J instant is called open if there is at least one unmatched edge incident to the vertex of consideration in that instant. Otherwise, the instant is called closed. Let's see. Let's look at, let's draw it again. We'll consider this word again. Let's see. So you have 1 to 2, 2 to 3, 3 to 1. This is a type 2 instant, and whenever you arrive at that point, there is at least one unmatched edge which is incident to that vertex. So this 1 to 2 is open. This 1 to 2 is unmatched. So we call it type open. Okay. Now we go down to 1 to 3 and 2 to 4. We could jump, but we do not jump here. 2 to 4 and 4 to 3. Now, if we look at, this is also a type 2 instant, but now if we look at the edges incident to that vertex, this 3, 2 and 3, 1, both are matched when we appear at this vertex. So this is a closed instant. Now, if we want to jump, you cannot jump because there are no options here, right? That is why the closed name is. You cannot jump here because there are no options. But when you just recall, if we ended here, if you wanted to jump, you could jump because that's what we did here, like close the 1, 2 edge instead of that. But if you encounter a closed instant, you just cannot jump. So now let's draw the rest of the part. So 4 to 3 and 4 to 2 and 2 to 1. So this is a very basic observation. So it is more or less an easy exercise to prove whenever we jump in the Dyck path, it has to be a level of type J open instant. So it is natural to keep track where the jumps occur. It turns out that the jumps can be explained through a much smaller subword of the main word, which has typical length of order n to the power 1/3 and easier to analyze. We call this edge the skeleton word. The skeleton word, the idea of the skeleton word came naturally to me, and I did math with it. However, formally defining the skeleton word, I had some difficulty. So the definition of the skeleton word is in the paper is not fully correct. I will tell the right definition here. So in this talk, we instead of formally defining the skeleton word, we shall explain it by the board word. So let's do it. And to make the picture clear, we choose not to jump. Because the picture will unnecessarily complicated. So we start with the following. We start the random walk. We continue until we encounter the first type J instant, and we consider all the edges open at the instant. So let me draw instead. So let's so I am drawing some semicircles. I will tell you in a bit while. So let's draw something. Okay, I will explain this in second. So suppose this is a type J open instant, type J open, and which is repeated here. So these are the edges which are unmatched until the encounter type J open instant. As this is a Dyck path, these semicircles are just Dyck paths themselves. So this is what we represent by the Dyck paths. Now we'll keep track of these open edges. So in the next step, you will cover another Dyck path, and then it might jump, but for this picture, sake of the picture, we will not jump. We'll keep track where these edges are closed. So we'll say we close some edges for some times. We close some edges for some times and do something, and then so then we again create some edge. We of course in middle of every edge creation there is a Dyck path. So we create an edge and we encounter another type J open instant. So this instant can be this vertex, this type J open, this vertex open, this vertex can be anywhere here or here, it doesn't matter. Okay. So this is how the skeleton word goes, and I will not there is a little bit complication there. That's why we made a mistake in the definition. So there is a little bit complication if you have edges repeated multiple number of times. So if you want, I can give it the definition, but this definition is good enough. Or if you have all the edges traversed twice. As I am running a little bit out of time, so is it fine? So let's describe some properties of the skeleton words. So let's describe here some properties of the skeleton words. So first property is skeleton words will typically will mean what is typically skeleton words will be typically of order n to the power 1/3 of order n to the power 1/3. So this is the typical length of the n to the power 1/3, and there typically there will be only finitely many jumps. Typically, again typically there will be only boundedly many jumps. Typically there will be only boundedly many jumps. Will be only boundedly many jumps. Many jumps. Oops. Okay, I hope you understand this. And third is all type J instants in the skeleton words are actually type 2. So these are also typically all type J instants are actually type 2 are actually type 2. Type 2. Oops. Type 2. So in particular, the skeleton words will be much simpler than the Dyck path itself. So it looks like this. So it will again be a Dyck path if we have all edges traversed exactly twice. But it will be much smoother than a Dyck path, typical Dyck path. So this will look like this. There will be finite jumps, and there will be only finitely made spikes. So these vertices, say I have drawn it at 3 spike, and these vertices are of type 2. So here there will be another vertex in the middle of the one of any upward segment, and this vertex will match to this. There might be somewhat here, and this will might to this, but only twice. So not more than that. So this is the typical property of the skeleton words. And how do we enumerate? Enumerating is like this. We give a word, given a word, we divide it into the skeleton word and the semicircles. We call it DW because they are the Dyck paths. And if we have no constraints on the semicircle, so but we know that the total number of edges traversed are constant. So this is how the power of the Catalan generating function of the Catalan number comes into play. And these are the Dyck paths. And what we do, we fix the skeleton word and enumerate all the possible Dyck paths. This will be a function of the generating power of the generating function of the Catalan numbers, and then this will give some weights on the skeleton word. So we sum it like this. So SW comma DW, and the expectation of this is finite and bounded and so on. So I am just writing 1 by 2 to the power something. So because all the edges are traversed exactly twice. So this will be and sum over 1. So this will be the cardinality of the Dyck paths. This will be cardinality of the semicircle. So this will give a weight on the semicircle. So this skeleton word. So this is sum over skeleton word times weight on the skeleton word, and then and this is like this decays exponentially in general for two complicated skeleton words. So we'll sum and we'll throw out two complicated skeleton words. Only this word survives, and we get something bounded. This is how the proof goes, and this is more or less it. Okay, and now we summarize. So these provings, we throw away the two complicated skeleton words, and these are very difficult generally. We have to keep a lot of bookkeeping, and we have to do a lot of bookkeeping and things like that. So we at first introduced the problem of edge universality of Wigner matrices. In this talk, we showed how the large power of trace, in particular order of n to the power 2/3, can be used in proving edge universality. We then used a combinatorial method to analyze the large power of the trace, and it is based on mapping words to Dyck paths, and probably some edges removed from it. This map is not one-to-one, and the exploration of Dyck paths, there might be jump. In order to systematically analyze the jumps, we introduce a subwords of we introduce a subword of the full word called the skeleton word and explore some properties of this. The final analysis is done in 2 steps. firstly analyzing the part of the word which have no jump, and then analyzing the skeleton words. That's what I told. Like part of the word which have jumps, which have no jumps, are just semicircles. And this is the key reference. So this is on archive. And thank you for your attention. Any questions?
So just to get an idea of the path form, when you explain the power of the trace, you have the products of random variables. Right?
Yeah.
Indices. Because the it is a matrix. And that is how you get these paths.
Yeah.
And the reason why only powers of 2 survive,
Yeah.
is because you scale the square root of that.
Yeah.
And so if you have sufficiently high power somewhere, then the sum is dominated by the rate goes.
Yeah.
They're basically right.
Yeah. So only random variables which appear exactly twice in this product survives. Yeah. 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 Heuristically, you can think it as a Dyck path because they have the non-trivial contribution. Heuristically, you can think it as a Dyck path, and in the Dyck path, every edge is repeated exactly twice. So that gives you the expectation, and that is 1 over 2 to the power k, and that cancels the 2 to the power k part in the Catalan number, and everything is bounded. So heuristically, you can think it like that. Oh, universality. So what we prove in the words, every edge is which dominates the limit, every edge is traversed exactly twice. So this expectation is universal, right? Whenever you have mean 0 and variance 1, 4 or 1, whatever. So that's why the limit is universal. That's why it is called universal.
You can start with any
Yeah, any distribution. This proof works for only sub-Gaussian, but in general, I think the result is known for finite foot movement. Okay. So what, in order to do this, you have to, by this method, you have to do truncations and things like that. So that would be a very laborious kind of work. Yes.
further questions.